Good morning. Today we'll start with compressible flow, one-dimensional isentropic flow. During flow through many devices such as nozzles, diffuser and turbine blades, passages, flow quantities vary primarily in the flow direction only, and the flow can be approximated as one-dimensional isentropic flow with good accuracy. Therefore, it merits special consideration. Before presenting, we will discuss this example. You can see here, this is your nozzle. So gas flows through this nozzle, varying current cross-sectional area at a mass rate of 3 kg per second. The carbon dioxide enters the duct at a pressure of 1400 kPa and 200 degrees Celsius with a low velocity. The velocity at the inlet is very low and it expands in nozzle to a pressure of 200 kPa. That is the outer pressure. This is 200 kPa. The duct is designed so that the flow can be approximated as isentropic. This whole process is, during this process, the flow is isentropic. Determine the density, velocity, flow area and Mach number at each location along the duct that corresponds to a pressure drop of 200 kPa. Means we have to find density, velocity, flow area and Mach number at this point when your pressure drops from 1400 to 1200, then 1000, then 800, and this 767 is your throat, and then up to 200. So you have to find this parameter: density, velocity, flow area and Mach number. So for simplicity, we use specific heat is equal to 0.846 kJ per kilogram. K is equal to 1.289 and R is equal to 0.1889 for carbon dioxide. It is taken from table. Now at the inlet, velocity is very low, so stagnation temperature is almost equal to the temperature. Because velocity is low, so this temperature, stagnation temperature, which includes the kinetic energy of the fluid, is almost equal to the T1, 200 degrees Celsius. Also stagnation pressure is also same as the pressure at the inlet. Because at the inlet here, this area is very large, the inlet velocity is very marginal. So stagnation temperature and pressure are same as 1400 kPa and 200 degrees Celsius. We know T0, P0. Now we have to find when your pressure is 1200 kPa, when your pressure drops to 1200 kPa, and corresponding to that pressure we have to find velocity, density and area and Mach number. So first we will find what is temperature when your pressure drops by 1200 Kelvin. So we know from the relation that for isentropic process, this is the relation: T is equal to T0 pressure ratio raised to power gamma minus 1 by gamma. When you solve it, the temperature drop after a drop of 1200 kPa is 457 Kelvin. Means in this nozzle, this is 1400. When your pressure drops to 1200 Kelvin, 1200 kPa, and corresponding to that pressure at this point, what would be the temperature? So temperature is 457 Kelvin. Now we know that this is the relation for stagnant temperature and temperature and velocity. So we can find velocity here. If we know T0 and T, we can find velocity. So velocity here is under root 2 Cp T0 minus T, which is 164.5 meter per second. We had got temperature, velocity. From this relation, density is equal to pressure upon RT. Pressure is 1200 kPa, temperature is 457. So we got density. We can find area. Mass flow is given. So mass flow is equal to density into velocity into area. We can calculate area. Area comes out is 13.1 centimeter square. Mass flow is given 3 kg per second. Density we had calculated just here, and this is your velocity which we had calculated here. So when you put, you will get mass flow rate you can say you will get area of the duct at when your pressure is 1200 kilopascal. Means we have calculated this area when your pressure drops to 1200 kilopascal. So corresponding that we have calculated this cross section area of this converging diverging duct or this nozzle. Velocity of sound or velocity of speed of this gas, that is calculated KRT. We know temperature, we know R for CO2, and we know K. So you will, it is 33.3.6 meter per second, and Mach number, that is your velocity of the gas to the velocity of the sound. So Mach number is 0.493, and these are calculations we had taken here for 1200 kilopascal. We will repeat this calculation for 1000 kilopascal, then for 800 kilopascal, and up to 200 kilopascal for 200 kilopascal of difference, and we tabulate all this value here at 1400 kilopascal, temperature, velocity, density, speed of sound, area, then your Mach number at 1200, then 1000, then 800. So here you can see this is a special case, which is, you can see, beyond which area starts to increase further. You can see here area is continuously decreasing up to 767. So this place where the area of duct is minimum is called throat, and beyond this you can see here area is further increasing. So that's why this nozzle is called converging and diverging nozzle, because first area is decreasing, it's converging, then it's diverging. So these parameters are plotted in graphical manner with respect to drop in pressure at inlet of the nozzle at 1200 kilopascal, 1000 kilopascal, at a throat which is 767. You can see the velocity of gas is increasing throughout the nozzle continuously. Temperature is decreasing continuously throughout the nozzle. Temperature will drop. Density will also drop throughout the nozzle because gas is expanding, so density will decrease. And area is, you can say, first decreasing, means it's decreasing, and it will reach a minimum value. Then again area start to increasing. We note that the flow area decreases with decreasing pressure up to a critical pressure value where the Mach number is unity, and then it begins to increase with further reduction in pressure. So when you reduce pressure further, it will start to increase. The Mach number is unity at a location of smallest flow area called throat. So this is portion where area is smallest, that 767 is called throat, and Mach number at this area is 1. So Mach area here is 1. The increase in velocity past the throat is due to the rapid decrease in the fluid velocity density. You can see density will drop very at a faster rate. So due to decrease in density, the overall volume of the gases will increase. So that's why even at the low pressure we have to increase the you can say cross section area of the nozzle. The flow area of duct considered in this example first decreases and then increases. Such ducts are called converging and diverging ducts. These nozzles are used to accelerate gases to supersonic speeds and should not be confused with Venturi nozzles, which are used for incompressible flow. The first use of such nozzle occurred in 1893 in steam turbine designed by Swedish engineering, and therefore converging and diverging nozzles are often called level nozzles. So you can see in this here, this portion is called throat, which is the smallest cross section area in case of nozzle. So this is converging diverging nozzle, and it can be converging only. In case of converging, this is your throat. So it is clear that the coupling among the velocity, density and flow areas for isentropic duct flow are rather complex. In the remainder of this section, we investigate these couplings more thoroughly, and we develop relations for variation of static to stagnation property with the Mach number of pressure for pressure, temperature, density. We begin our investigation by seeking a relationship among the pressure, temperature, density, velocity, flow area and Mach number for one-dimensional isentropic flow. So this is a mass flow rate, that is density into variable velocity. So differentiate this. When you differentiate, and after differentiate, divided by this quantity. So during differentiation, when you take the derivative of density, these terms remain constant, plus derivative of second term, and the rest will remain constant, plus derivative of this volume with respect to volume, and during that derivative this terms remain constant, and you will get this there after differentiating. Now for conservation of energy, for steady flow, work is 0, heat transfer is 0, because it is adiabatic, and tension is 0. The equation becomes h1 plus v1 square by 2 is equal to h2 plus v2 square by 2. It means this is your constant, or if you take the derivative of this will become dh, this will become v dv is equal to 0. And from TDS relation we know also this TDS is equal to dh minus vdp. This is isotropic process, so ds term is 0. It means dh is equal to vdp, or instead of here v you can write 1 by rho, so dh is equal to 1 by rho dp. Now dh is equal to 1 by rho dp, you can replace here, so this relation become dp by rho plus vdp, which we had written over here. So neglecting the potential energy, the energy balance for isotropic flow with no work interaction can be expressed in differential form. So you, when eliminate dv, what you have to do, instead of dv here you have to replace this dv, and you can use this equation. So find dv from this equation and put here, and after solving what you will get this equation. Combining this equation and this equation, you will get this 1715 equation. So we had already developed one equation, that is your velocity c square, velocity of your sound is equal to del p by del rho at isotropic. We can use this equation. So replace this term, because this is isotropic process, so replace this term in terms of c, and on rearranging you will get, you can take 1 by v square out, so here you will get, so when you take 1 by v square out means you have to multiply here, and v square by c square here, that is called Mach number. Now you can see here this is a relation between change in area of the duct and change in pressure. So this is important relation for isotropic flow in ducts, since it describes the variation of pressure with flow area. We note that area, density and velocity are positive quantities, and if your Mach number is less than 1 means subsonic flow, the term is always positive, and dA and dP have the same sign. So that is, pressure of the fluid must increase as the flow area of the duct increase. If your pressure, you can say if your flow area of duct will increase, this is positive, the pressure will increase, and if your pressure area of duct will decrease, the pressure will decrease. It means for converging ducts the pressure will decrease, and for diverging ducts, which is called diffuser, the pressure will increase. For supersonic flow means Mach number greater than 1. If Mach number is greater than 1, this term will greater than 1, so this term will be negative, and it will you can say reverse, means with increase in area the pressure will start to decrease, and the flow area of duct decrease, then your pressure will start to increase, means reverse. Thus at supersonic velocities the pressure decreases in diverging ducts and increases in converging ducts. Another important relation is, if you replace that above term by this relation, means find dP, and this replace this dP here in terms of dP from this relation. When you replace this dP in terms of dP, you will get this relation in terms of change in volume. You can see here, if Mach number is less than 1, this area dA by dV is negative, and for Mach number is equal to 1, this dA by dV is equal to 0. Thus the proper shape of nozzle depends on the highest velocity desired relative to sonic velocity. To accelerate fluid, we must use converging nozzle at subsonic velocities and diverging nozzle at supersonic velocities. So the velocity encountered in most popular applications are given below. So this is the variation of flow properties in subsonic and supersonic nozzles and diffusers. Subscribe this channel, like this video, and thank you for watching this video.